So, welcome everybody to the ICT webinar series. Today we have two presenters, and they will introduce themselves. And so, please go ahead, Kerry.
Hello, I'm Kerry Slattery. I'm an assistant professor in the Technology and Construction Management program at Missouri State University. Our presentation today is based on a project that we did for ICT. It was just a one-year project in 2010 and 2011, and we were presenters in the poster session at TRB for the high value DOT research project. So we'll go over there. It's called Expert Systems Approach to Highway Construction Scheduling. The research was fun. The idea was to it was routed through the construction branch of IDOT in order to try to help engineers prepare more realistic construction schedules. So when they set the requirements in the contract for project duration, it's something that challenges the contractor, but also doesn't make it so short that it adds a lot of cost. So the way we approached it, our objectives were to interview both people that work for construction firms, engineers, and also various resident engineers at the different district offices of IDOT to get information on how they did scheduling and some things about production rates. And one of the things we really wanted to look at was how weather data is used to determine the number of working days and when something is a working day. Especially since Illinois is such a tall state, I guess, north-south, weather varies quite a bit. So instead of having a fixed winter exclusion period for the whole state, it would make sense to look at what activities could be done earlier in, say, in southern Illinois. And we put all this together into a tool that brought the information together and helped to make some quickly create schedules and make it something interactive, so it's easy to change things and see what happens if we change an assumption. So our approach was not to look at everything in a construction project, but just look at the activities that would fall in the critical path, and then focus on those to try to determine what typical production rates would be, and also try to look at how that would be determined. Especially for a larger job, you would have a larger crew or more crews, and some of that had to be considered. We also wanted to look at most of our templates just look at a series of activities, one after the other, but we do look at some places where there are activities that can be performed concurrently. So obviously, you can get done faster if the scheduler plans that. And again, we identified the activities that were temperature dependent based on the IDOT specifications, and used that to help define based on the location of the project when the likely times would be that they could do those activities and when it wouldn't be. So instead of just using our 5-month winter exclusion period, we could be a little more account for the different parameters that affected that activity. Right now, the number of working days that they expect per month is based on some expected number of rain days per month. So we studied that and looked at how that compared to what we current number of working days. We found it's pretty uniform across the state, and I think we think it's well reflected in what they do now for working days. And we know there's other things that can affect schedules. They're site specific, so we made a provision that the scheduler could look at, especially specific activities that have other schedule constraints and identify those. So this is just a list of about 40 or 50 things that we thought could be controlling items on a IDOT type project. Then we plotted out how the winter exclusion period for Illinois compared to neighboring states, and we found Illinois is pretty conservative. I think it probably has the longest range of 5 months, and it starts a little later than some of the northern states, but then it actually goes as late as any of the states in the Midwest region. So and most people find this. There's a whole lot of construction that goes on, a lot of projects inside of the winter exclusion period. So it definitely is something that could be studied and possibly modified. We looked at, we got temperature data for average temperatures at many locations in Illinois, and we looked at all, when you look at temperature data, you get the average, the minimum temperature on the day, the average temperature during the day, and the maximum. And we thought for some activities, we might base when we could and couldn't do it on, what the minimum, making sure that the critical temperature is greater than the minimum temperature. But others might just be based on average temperature. If it's going to be around 45 degrees that day, it might be okay to do an activity that required a minimum 45 degrees. So it's up to the scheduler to decide which of those to consider. we studied what the average number of rain days were per month, and again, it's pretty consistent across the state. Southern Illinois gets a little more rain in the spring, early months, January, February, March, than some other parts of the state. So we just have one model for that. The question is, what level of rain event per day would be a non-working day? And it seems pretty conservative, but what works out now, really the 1/10 inch per day. So in May we have an average of about 6.5 days with more than 1/10 of an inch, and that seems to correlate fairly well with what IDOT currently figures as far as what they would expect the number of rain days to be in a month. And I believe that some other states also use the same parameter if it rains more than 1/10 of an inch. Of course, there's a lot of things. Sometimes a 1/10 of an inch of rain for some things won't be as critical as others, but that ends up being a fairly good threshold value to look at for determining how many rain days you would have per month. So in the expert system, we tried to take this information about weather and rain, and then also temperature data, and also start to incorporate information to help the scheduler make decisions on what production rates to use, what durations then to consider for the different activities, what order to expect to do the different critical activities of the project in. So first thing we did was develop some schedule templates with our TRP. We identified 12 kind of common projects, common project types that we focused on for creating these templates. We tried to get as much information as we could to help determine production rates, but in some cases, we put in some extra, some simple calculators to help based on different parameters to help the engineer that's trying to determine the duration, calculate what it would be for a project. And then we assembled production rate data from various sources to also provide that in the tool. So we don't try to tell people exactly what to do. We try to provide them with the data that we've collected, provide them with a description of how a typical scheduler would look at this project and determine what the production rate would be, and let them apply that as best they can to their project. And these templates that we have right now are all fairly simple, but we have a provision in there that if several people are using this and want to share and improve templates, it's a common standard data format, and that could be done easily. So these were the 12 kind of standard road construction or construction projects that we developed templates for. There's not any there could be others. Maybe some of these wouldn't be that common, but that was the ones we agreed to work on with our advisory board. And for production rate data, so for those 46 or so different types of activities we thought might be critical, we provided information like this in the program. So when they click on that activity, they can see some information about how contractors usually determine what the production rate is. It's usually based on what the rate they can get per day or per hour is from their asphalt plant. In this case, we did put together a calculator so that whereas we might want our production rate in terms of square yards per day, here we tried to help them convert from 200 tons per hour to square yards per day based on various parameters about the pavement. And also here we've shown what the current IDOT BDE manual says, and the problem with many of these, because there are so many variables in determining production, there's a wide range of values from 1,000 to 3,500 square yards per day. And we had several other sources of information that are referenced in our report that gave other values. So there's a lot of variability, but some of the best information we got, I think, was from District 5 or 6, and they really had a lot of good data on asphalt production, paving production rates. So we provided information for the various critical activities to help determine the production rate. Software, when you run it, it allows you to set up information about the project. We did have it where when the engineer is looking at this, they're usually focusing on a certain letting date they hope to have this out for. So based on the letting date, we calculate the expected start date. They select the project type, and then they are able to look at the template that we've developed for that type and make modifications to it, because there's always going to be some difference on a job. And then we let them set up a calendar for the job. So depending on what they expect to do as far as 2-day weekends or possibly 1-day weekends, what other constraints there might be on the project, they can they can set up a custom calendar, and it also involves selecting the project location so they can see what the what we would expect the temperature-based constraints to be on various activities. So, this is the really simple form when they open the project, put in the project information. But again, they select the letting date, and based on typical, number of days you expect to award after the letting date, and then the number of days we expect before the contractor starts, it calculates the start date. So that's, again, the starting point. Then based on the type of project, on one of those 12 templates, it gives a the typical activities that we would expect to be critical in that, and the order they would come in. So again, this is really a simple template, and that all these activities are just in a series. So when mobilization is finished, we start with tree removal and excavation. So that's again a fairly simple but standard template. But they are able to modify that in the software. So here we're just showing we could have a lag or lead between two activities. So I made earth excavation could start 4 days after tree removal starts, and placing the shoulders might be able, not be able to start until 3, 4, and 7 are completed. So again, it's fairly simple. I think most people have access to Microsoft Project, and we try to use a similar format for identifying the predecessors. And we can also add activities. So if they something after pipe under drains they want to add in, they can select from the 40 or so activities that we've programmed in to make modifications to the schedule. So we've given some standard templates, but we want them to have the flexibility to work with those. And this is our calendar. This is kind of the default calendar, so we would expect 2-day weekends using standard holidays. By rain days, we mean we went with the standard number of working days expected each month based on the BDE manual. And we're going to, for the winter exclusion, we said we're just going to use the December 1st through April 30th winter exclusion. So we can, so that's the standard. So it won't allow us to work on those days. And the rain days, if there's 6 in a month, it just randomly assigns those. And if they happen to fall on a weekend, that's okay. It just, in the end, we lose about the correct number of working days based on the historical. What IDOT's always figured on these. So we can add constraints. So we might add some additional holidays if there were any. We could go, instead of the BDE manual, we could go with the this historical rain data. And again, it's very close to what's in the BDE manual. And we could eliminate the winter exclusion period if we wanted to just look at temperature-dependent activities. So we can modify those. And then the other ones here, our favorite one to talk about is critical habitats, because we know that at least some parts of the states, you can't cut trees after a certain date because the bats are nesting in them. So that's something we can add in, these, and just show what day, what the restricted days are, and if they affect all activities or just certain activities on the job. So we can assign, specific constraints to one or more activities. Then the other capability we have is to go ahead and say where the project is. So we identified this project as there's a little plus sign there, right where I think Springfield is. So if it's in Springfield, on this project there were 4 activities that had some required minimum temperature for in order to be able to do those activities. So those are listed here. The temperature constraint based on the the specifications is given, and then it determines what range of days we can't do those activities based on the average temperature over the last 22 years, I think is what we looked at. So it doesn't say that we know that there may be days earlier than that it's going to be too cold. There's also going to be days later than that it'll be warm enough. So this is kind of the average and what we'd expect to be the days we wouldn't be able to do certain activities based on the temperature requirements for performing that. This is where I said we could base this on the minimum daily temperature, the average daily temperature, or even the maximum temperature. So it's depending on the judgment of the scheduler. It's minimum would be conservative, but maybe some activities, if we just looked at the mean temperature for the day, that would be again adequate. They could get work done afternoon or something that day. So so the software then, after we set up our the constraints on schedule, It then provides us with a simple bar chart schedule. Again, most of our templates just involve one activity after the other. And then each activity we need to identify what we want to determine the days it's going to take to complete that. So it's obviously going to be based on the quantity of whatever we're doing for that activity. We provided different calculators and some information on production rates to help determine how much could be done by one crew, and then at their discretion they might realize it's a large job and would expect the contractor to assign multiple crews on some activities, so they can change that. So the scheduler can put in a number of crews, and also there's a provision just to type in notes so they can record what it is they thought about and why they made that decision. We did put in a couple provisions for what I call multi-layer schedules, where we can break some activities down into more refined, more sub activities, and at some point they can modify the start date if there's a change to that. So this is our bar chart schedule that shows in this case I had just enough room on the screen to do 9 of the activities, and we use some color coding to identify what the different days meant. So yellow or orange is what we're considering to be a working day. We blocked out the weekends, we blocked out the holidays, and so forth. So again, the rain days are just, if there's 6 in the month, we schedule one every 5th day and see where those land. And at the bottom of here, as I'll forget to point out later, is where we do show, based on our schedule, the completion date, number of working days, and number of calendar days. So any one of those 3 or all 3 of those might be of interest. So we can edit an activity. We already saw one about asphalt paving before, but we have our quantity and what we expect the crew production to be. And at this point, they could, if it's just taking too long or it's a large job, they can change the number of crews and to what they would expect a contractor to use if they were to be working on this job. So we go through our initial schedule, just kind of assume 5 days for everything. But now after we're done, all these durations turn to green, which means that we have considered each of those and come up with what we think is a reasonable duration, and we can see the what the total project duration will be. So again, these numbers at the bottom are updated as far as completion date, working days, and calendar days. And of course, it's very simple to go back and look at one of these activities and modify our assumptions or change something, or if we're almost done and then we hit the winter exclusion period, we might go back and again reconsider how we expected the contractor to perform that and see how that affects our schedule. So this gets kind of complicated to digest, but we did want to do some other refinements. So we have both you can put in activities that are done in series or in parallel. So in this example here, we're placing 2 spans on a highway overpass. So that whole activity is considered a master activity, and we break it down. There are 2 things we do in series. So we do activities 1 through 10 are completing the first span, and then activities 11 through 20 are completing the second span. And these are also broken down with other, we call a parallel set of activities, where when we're putting in the piles and placing abutments and placing pile caps, it makes sense we schedule that for that pile driver to start on the piles on the east abutment, and then put piles on the piers in the middle of the span, and then we move that pile driving crew across, and then the other crews follow behind. So there's a lot of overlap in those activities. So a contractor that's trying to meet a challenging schedule will do it that way instead of doing everything on the abutment and then moving over and doing everything on each pile group. So that's we tried to make that easy to do and encourage people to look at it that way. So for summary, we developed this tool as a way to synthesize information from a lot of different sources. So when a engineer that's putting together these plans and trying to calculate a reasonable number of days for construction tries to put this together, they have some assistance. They have a way to help them do it more easily and get more information and help in applying that information. We do want to encourage sharing of templates as more people start to use this. So people that have a lot of experience with this can share that across other districts. We have the capability to really look at regional temperature records to really get a better idea for when we can do certain activities. And it's always some of the people, when we did some of the testing on this, they thought it was kind of fun. If it's easy to make changes to assumptions and see what happens, people are more likely to do those things and really think harder and model several things until they get what they think is a good model. So we are about to start a second phase for this. You know, the most difficult thing here is to really determine what is a production rate. So obviously the production rate depends on the contractor, how many resources they commit to it, and there's a lot of different types of activities. So what we plan to do in our next phase is to mine the data that's been collected over the last few years, a couple of decades, I guess, in the I-Core system, and try to synthesize that into better information based on historical data to help them determine what are expected production rates, based on things like the job size. Again, excavation, if it's a large job, you would have a lot higher production rate than a small job because you would commit more equipment. And part of this also, we are going to visit the districts. We're going to do some training on the software in the districts, and just again try to by visiting projects, get more insights into how to put this together. So that's my last slide, and about my time is up, so I'm ready for questions.
Okay, I am now going to mute everybody. If anybody has any questions, you can speak now. Okay, looks like we have no questions, so now we'll continue with our second presentation. So we can start sharing their screen.
Stop sharing.
Yeah. Thank you.
Unless it's a car, then it's a screw, but what's it? Can you try? This in here?
You're not?
Yes, yeah, we're here.
Okay. You can start your presentation now.
Yeah, I'll Microsoft PowerPoint right here. What's hide stage there? How come it's not showing? Can you see the presentation?
Yes.
Okay. Oh, so we don't see it in there. Okay, good. Oh, okay. Well, good afternoon, everybody. Can you hear me well?
Yes, I am getting two screens. Do you have two monitors, perhaps?
Yes, we do. Should we?
Yeah, just share one of them because right now I can see both presentations. I see both screens.
How did you do this?
You can just share that program itself.
Right, that's what I thought we did. And how did you get to this? Automatically. No, that would stop sharing. Did you run this one? Yeah. Is that what you did? Well, we can, in that case, let me see. Do you see it now on just one screen?
Yes.
Okay. We may have to go to a two-screen situation to run a video, or actually we may not have to. We'll be able to run it this way too.
Okay. Yeah, that's fine.
So, okay. Good afternoon, everybody. My name is Suhail Al-Huwar. I'm associate professor with Bradley University, and with me I have Dr. Inad Mahmoud here. He's an assistant professor at our department. We both have been working on this project called Performance Evaluation of Snow and Ice Plows. Our presentation is a little long, so I'm going to try to go a little bit fast and try to cover all of the aspects of it. Basically, the project is being funded by ICT and IDOT, the Illinois Department of Transportation, to study the performance of plows and snow plow and take some measurements on plow blades, basically trying to improve that performance or finding ways of improving the efficiency of the operation and learning more about the performance of the plows themselves. We had the task are to conduct a comprehensive study to evaluate the performance of the snow and ice plows, and then also develop, to achieve this, we needed to develop an instrumentation and data collection system for these snow plows. And we considered two types of plows, both front and belly mounted plows. And then also one of the objectives is to develop a synthesis of best practices in snow and ice removal. Really what we did, the proposal itself had these, but we sat down and also we defined the scope with our with our chair, with the TRP chair, Tim Peters from IDOT. He's been quite a bit involved with us and very helpful. So we really sat down and talked about the tasks, and these are the tasks that we came up with and defined the scope for. And basically is to do a literature review and synthesis of best practices, to develop a performance evaluation procedure, including finding ways to instrument the plows and the calibration installation of the instruments, perform some field tests in actual snow conditions, and then develop finite element models to synthesize the analysis or to verify the analysis and try to come up with more data based on computer analysis then. And then documentation of the project activities and findings. These are a couple of pictures of the plows. The first one is what we call Alaskan front body snow plow that we're using. And the other one is the underbody scraper. Both of these plows are actually mounted on the same truck at the Morton IDOT facility. And actually I want to take this opportunity to really thank all of the people who really have been helping us out. They did a great job helping us out with these. Instrumentation, we included 22 strain gauges with their signal conditioning modules and 2 data acquisition systems that were installed on the truck. We also have some video cameras that we installed on the truck to keep track of the snow plowing activity. I will show you in a little bit an example and show you also the reason or the usefulness of having that video available. This is a picture of the box that we made to keep all of our instrumentation in one place and protected. So you see what you see there, the gray, where my cursor is, if you can see my cursor, that's the signal conditioners, and then the black box, that's the data acquisition system. We had 22 strain gauges, as we mentioned. 16 of them are mounted on the front body plow, and 6 strain gauges are mounted on the underbody scraper. Wiring was kind of a challenge, so we had to really do that carefully. And what you see here, we also have 2 accelerometers to measure the inclination of the underbody scraper. So these accelerometers are installed on the underbody scraper, and what you see here on the right-hand side is a small metal box that we put there to protect the accelerometers. And you can see the cabling on the left-hand side. And we calibrated the accelerometers using the different positions of the plow, measuring them physically and verifying that we are actually getting the correct, and I mean, that's what we mean by calibration. They come really calibrated, but we needed to verify that we were getting the correct information, so we did the test. The strain gauges, we also verified them by installing them on steel W shapes and loading them in the lab here at Bradley. To install them, we had to do a lot of sanding, you know, to basically make sure that the surface is clear and clean before we put in the strain gauges, and these are just bolt-on strain gauges. So the instrumentation, we have 8 strain gauges installed on the carrier structure, 8 strain gauges installed on the plow, and as we mentioned, the members were sanded and cleaned before. These are pictures of the carrier on the left-hand side, or the driver's side, and you can see the strain gauges attached and the cabling to them. So. And here's the passenger side of the front body plow. We had to really be careful on how to wire these, and developed a way where we can just plug them in from one side into the other. You know, there is a problem if, for example, the driver is removing the plow and they forget to unplug it, then you have all of those cables basically disconnected and sometimes broken. So you have to be very careful. But there also, we found out that, I'll show you pictures of the plows after plowing. It's a very corrosive environment, very tough environment, so many of the cables we had to replace. This diagram shows the locations of the strain gauges on the front plow and the carrier structure. And these numbers are very important because we have to know which strain gauge is attached to which sensor and which channel number, so when we collect the data, we know exactly where it is being collected. And this is a picture of the box in the cabin, the truck cabin, with the instrumentation in it. And this is inside. Again, another picture of the instrumentation. And this is what it looks like if you're driving the truck at night. You want to see all of those lights on. If any one of them goes off, it means that one of the cables was broken or something wrong is happening there. So. And this is the underbody scraper. And this is a video. See if I can run it in preview mode. This video actually was taken by handheld camera. And this camera was supposed to be installed on the back of the truck to show the back side after plowing, but it didn't take us very much time to realize that it was not working well, because within a few minutes the video gets covered with snow and then you don't see anything anymore. So that part of the plan didn't work well, but we do have a front-mounted camera that is actually mounted inside the cabin, and this is the one that we're going to see right now. So this is actually plowing during the night. And what you want to pay attention to is, see, this camera now is fixed to the truck, so when you see the motion of the plow, that's just the plow independently of the truck. That's the plow moving. And why is this important for us? What you see here is a collection or one sample of data points that were collected from one strain gauge, okay, covering a 3-minute span. It's a lot of data that we have. So we broke it down. We have students working on this and breaking it down into segments of time. And these 3 minutes, we're collecting, in this case, we're just showing the raw data from the strain gauge in millivolts, but we can change that into, and we will change that into stress using the appropriate calibration factors. And we have students go through this data. The video that we take is time-stamped, and the data is time-stamped. So by synchronizing the data, the timestamp on the data and the timestamp on the video, we know we can tell what's happening at what time. So we have the students actually looking at the video during these time periods and trying to figure out what's going on. The first run we're doing is really trying to figure out the status of the plow, where it's at, which direction, is it up or down. Okay, this information is very, very important to us, because so we know whether the plow is really is plowing. When we look at the certain data, is it plowing at this time, or is it just hanging up? It's very important so we can study that data more efficiently. So what you see, and we want to know, for example, these data points that you see that go up and down here, we want to know what caused them. So it could be like, if you're going and you see on the video that there is a big shaking from the plow, it might mean that the plow might have hit something, or something of that nature. So that's really what we're trying to figure out. But the positions of the plow are identified by the student through the video, and that's why having the video is a very, very important component of this study. So they are able to say whether it's up or it's down, which direction it is, and so on. Okay. If you have any questions, please do not hesitate to stop me at any point. This is the underbody scraper showing the instruments on it, and that would be, this one has the strain gauges and it has the accelerometers also. And here's another picture where we put, if you look at these two strain gauges, you can see one of them is vertical, the other is horizontal, because we're trying to capture the state of stress in those two directions at that location. And then I will let Dr. Mahmoud now take over from here.
All right. Prior to taking the truck out to do snow plowing, we did a couple of dry runs and soil runs just to test the instruments and make sure everything is installed and working properly. The dry run was conducted in the Morton truck facility, so we wanted to ensure that everything is functional. The dry run consisted of lowering the plow into the pavement surface with the blade saver on and off, just to check that the strain gauges are able to capture the stresses and the strains and stresses due to that. So this is the dry runs data actually is not going to be useful in terms of analysis. All it is just to make sure that all the signals, that we're getting all the signals from all the different strain gauges. So in this graph, it just shows different signals getting from the different gauges. And again, this is a dry run, so something usually we will not encounter in a snowstorm, because usually you'll be plowing snow. And we're able to make sure that all the sensors are giving signals, and we're able to measure that signal. The next part, prior to the snow, we try to do dirt removal testing instead of snow, just to make sure that we're able to capture the effect of snow, or hopefully something similar to it prior to the snowstorms. Again, this took place in the Morton truck facility. First, we validated that the data collection procedure is working, and we tested the instrumentation and the data procedure. If you look in this graph, here we have signals with the on and off here. It just means that we have the saver, the plow saver on and off, and the plow saver function. So that's really helpful in reducing the stresses in the plows. If you compare the blue line here, it's showing that the saver is off. If you compare it to the case where the saver is on, let's say for the light green, you'll see a difference in the amplitude of stresses developing in the body of the plow itself. So this was really helpful, at least just to get a feel of how good the saver function for the plowing, or the reducing the stresses in the plow, which will also reflect in reducing stresses that could develop in the truck itself, which sometimes become really high severe, or of high severity. So the dirt removal, or the soil removal happen, as I said, in the Morton facilities, is just a picture of the truck in the front. This is actually one of the graduate students who's working with us through Dragoo, who has been also very helpful and has been in all the snow plowing operations at night. The next slide, we'll see a video showing that process. The video starts, it's actually showing both front and back cameras, and as Dr. Hawar mentioned, the back camera wasn't very useful, or we couldn't get useful information while a snowstorm is going on, because it will be covered in snow in a minute or less, and sometimes actually the lens freeze, so we can't see anything. But at least this is something that we can look at during dry runs and soil runs, that we could capture the back and front of the truck. So the truck is now driving to the area where the soil or dirt was located. And this was also part of checking that the videos are working. We'll be able to get videos that we can analyze and look at, and we've been working on analyzing these videos now. So this state, or at this state of the project, this was prior to the snow operations. So now you'll see the plow or the truck toward the soil. Now we can actually see the difference between when the plow is up and plow is down, and that's also what we try to do in the videos. And if you see at the back, you can look and check the efficiency, or how the dirt is removed compared to what it was at the beginning. The picture to the left is just the back camera. It's a GoPro camera that we used to capture that. The front camera actually it comes with a lot of functions that's been really, really helpful. It actually has two cameras, one that gives you the outside, and the second one is internal, so it can give you the drivers. So it's an inside camera view. It will also give you a GPS. So this all the files that come from this camera could be connected, and we can tell what GPS location. It could be embossed in a Google map. That also can help us in looking at the different routes, or if any incident happened, we can exactly know what location and what time it happened. It gives also the date, location coordinate, the speed of the truck, which is also very helpful, the date again, and it also gives some force and a control panel where we can play the videos back and forth. What we're mainly looking at is to collect the videos, the GPS, and the timestamp, which we can also correlate with the data that we're getting from the sensor, so we make sure we have collecting the data at the same time, or what's happening exactly at what time, and how is that affecting the stresses and strains in the plow. The next Next part we're working on is to start a finite element analysis of the data collected. So the stage we're at now is that we transferred the plows or the shape of the plows into finite element meshes using Abacus. The next step will be is to try to change the parameters and examine the effect of these changes on the analysis. So what that means is that we could try to apply different velocity, different angle of attack, and maybe different properties for the plates, just to see how that affects the efficiency of snow plowing. So this is a work in progress, and that's where we're at now. The next couple of pictures just shows what Dr. Al-Hawar mentioned a little bit before, is how severe the operation could be on gauges and cables. If you look, if it's this is the back of the front plow after several hours of plowing, you see that everything's covered with snow. We had cases where we lose some cables due to corrosion. So this is something we usually check after the next day, after each plowing operation, to make sure that all the cables are there, we didn't miss anything, and then if needed, the cables usually are replaced. This is again from the same snowstorm, but we're looking now at the underbody plow, and this actually is covered more with snow, and you can barely, or you can't even see the strain gauges that we have. However, with all that, the strain gauges were able to measure strains, and the accelerometers were also able to give us the inclination angle of the underbody plow. So with all that, we're really satisfied with the gauges we got and the casing that we have for them, and all the connections and all the cables. So that was very assuring for us at that stage. So as conclusions, or maybe summary of this study as we have it now, one thing we noticed or got to the conclusion of is that snow plowing is a messy and dangerous operation, which is something maybe the general public doesn't understand or even relate to. The instrumentation and data collection system developed was effective. We're able to assess several field factors. It was also able to withstand the snow weather and the cold and snow. The blade saver option showed a really significant reduction in stresses in the snow plow and the carrier structure as well. As we mentioned, both the plow itself and the carrier were instrumented. This was proved for the dry runs on asphalt, dry runs on concrete pavement, as well as soil dry runs on concrete pavement. High stresses in the plow are observed when we plow concrete compared to asphalt. Also, using the underbody scraper with the front body during heavy snow events is the most effective way for providing clean driving lane or cleaner driving lanes in less time. The underbody, again with the front plow, is very effective also in removing ice, more ice than just using the front or just using the underbody separately. That will also help in that the ramp could be then made less slippery by adding salt. Finally, the snowplow operators need to be very alert and need to have an excellent understanding of the equipment they're working with to reduce hazards to themselves and the public. And with that, we finished. This is the end of the presentation. Thank you for listening, and Dr. Al-Hawar and myself are here, and we'll be happy to get any questions.
Okay, thank you. Microphones are now muted, so if anybody has any questions, this is the time to ask.
We are also, I want everybody to know, we are also conducting interviews for best practices. So if you or anybody you know is involved in snow plowing and would like to contribute, just contact us, and we'll be very, very grateful to be able to perform an interview with you. And it takes about an hour and a half, and we can do it like over the phone.
Okay, it looks like we don't have any questions, so I want to thank everyone for joining and thank you for our presenters.
Thank you.
Thanks.